So let's take a look at convolutional neural networks. It's easiest to visualize this type of network and understand what it's doing. So let's go back and look at the vision problem on NUS data. Recall that the NUS data set consists of a bunch of handwritten digits, and they're arrayed in a raster image of 16 by 16. So I've simplified it down here to 8 by 8, but it's a similar idea. So here's the digit 6. What we're going to do is take all of these pieces of information and take each row and pull it out as a vector so that we have a long array of input nodes all the way from the first one, which would be up here in this corner, to the 8th one, which would be over here, 9 through 16 and so forth, all the way down to 256, which would be the last element here. Let's transpose these so that we have an easier topology to work with left to right, as we've done in several neural network designs already. We're just going to put it this way, and you can see again that we've just moved the first element here and all the 256 elements here, and this represents basically a line-by-line split, so that the first black parts of the 6 correspond here, the second parts that are black correspond here, and so on and so forth. Now I want you to consider what this means. This means that our inputs, 1 is actually going to be this node, x2 is going to be this node, and all the way somewhere down below is our x256, and we still have our bias term here. And these are being fed into the neural network. Let's take a look at this particular neuron here. This activation function is going to be getting these as inputs. But let's say we have tuned the weights in a specific way to only look at certain parts of the network. So for example, let's just say I've activated all these edges in blue and turned off all the edges here that are marked in gray. So I'd like you to answer in your notebook, what is this particular neuron now doing? Once you think you figured this out, let's do it again for another one. Here's another case of which we have another neuron, but the edge weights are different. You can see that only the top 3 edges in these 3 are being activated. And let's say all the other node edges down here also correspond to a negative weight. In this case, there's only 3 activations in each of the first 3 rows. So what do you think this is doing? Go ahead and answer this in your notebook. So the idea behind convolutional neural networks is to do something similar to what traditional image processing does by using a convolutional filter. You can take a look at this webpage, which actually gives the result as we showed here. It's much more interesting to look at, but for the sake of time, I'm just going to illustrate what we mean. Pretend we have a convolution, which is a 3 by 3 matrix, or an n by n matrix that we want to generate. You can see that the numbers here actually correspond to the times variables that you see in the inputs here, right? Times 1, times 0, times 1, times 0, times 1, times 0, etc. are all in the network here, as described. And then when the convolution filter goes through this, for example, in this top part of the network, let's compute it. It's just taking the kernel that we have over here and multiplying it against the weights at this point. So we have 1 times 1 times 0 times 1 times 0 times 1 times 0 times 1 times 0 and times 1. And then taking all of those and summing them together. So it looks like I have a 1 here, plus a 1 here, plus a 1 here, plus So 1 here, and all of the other ones are 0. So I'm going to get a 4 as an output. Since this particular position corresponds to the upper left-hand corner of my grid, I'm going to get this number 4 as the result of applying this kernel to this particular location to get this output at the same position. So we're going to call this the computation of a convolved feature that's based on a particular kernel, the kernel that we've illustrated on the left. And basically what we're doing is we're sliding this kernel, this 3x3 kernel, over the entire image with a stride length of 1, that means a step size of 1 as we go along, to compute the convolved feature. And this can be useful for edge detection and corner detection algorithms that try to recognize certain spatial features within an image. When we do these types of convolutional filters on the images at the low levels of a neural network, we get up very basic features just like you might have seen when you looked at the website that we referenced. For example, we could develop a particular filter similar to the one that we saw on the quiz examples that could be just vertical line detectors, basically activating when the filter is detecting a vertical edge over certain parts of an image. We could also get one that finds horizontal lines and sums that are small circles. Okay, maybe by having a filter that has a 0 in the middle and solid numbers on the outside of the filter. The important thing here is that these filters are for particular places. So what we want to do is find a way to make the calculation of these features invariant to their position. It shouldn't matter whether we find a line in the upper part or in the lower part. These should all be using a similar feature to engineer, right? Just like we would want to calculate manually or create a nonlinear transform to find a horizontal line, we would want our learned feature representation coming from the neural network to also embody it, but not necessarily in specific places. So we want to throw away this restriction. So this type of problem might come to be solved from a higher level neuron. So for example, let's say that we have a particular neuron here that's only activating with strong positive edges for the second row, another one that might be towards the middle row, and another one that might be towards the bottom. If it's in this case, what we can do is we can compose these together using the AND and OR gate idea that we saw in the neural network lecture to basically create another feature that would just represent the high level feature of whether a horizontal line is present. Similarly, the network could learn another type of feature corresponding to a vertical line, and even one associated with small circles in a position invariant way. You could then use these detectors to help with detecting whether a particular number is present or not. For example, the number 1 probably has a vertical line as a very strong indicator, and the number 8 might have a couple of small circles. So this is how neural networks in general try to learn unsupervised features. By learning a feature representation, and in the case of a CNN, this is best when the input space is locally structured in images that are spatially aligned, or languages or other time-sensitive signals which are temporally structured. In this case here, on the right-hand side, we're showing you an image that comes from an input image that maximally activates a particular neuron in the neural network. You can see here that at the low levels, it's picking off edges oriented in a certain direction with lightness or darkness patches. So these are low-level image features that come from the bottom of the network. When we look at higher convolutional layers, for example, the third layer up or the fifth layer up, you can start to see interesting things. On the left-hand side of each of these layers, for example, layer 3, we have the activation, just like we saw on this previous slide. Those are what the neural network weights are for a particular filter that is being computed. And on the right-hand side of each of these images, we see a particular picture that maximizes image that maximizes the strength of the corresponding units activation. So for example, this particular one here looks like a wheel. You can see that this particular wheel is maximally activated by this particular pattern. So it's a wheel on the left-hand side of a car bottom, similar to many of the other patterns that are activated in this image. So it's quite interesting because the lower level features that we can see are fairly simplistic, right? They are, for example, horizontal lines, as in this case over here, okay, or textures, as in this case over here. But at a higher level, for example, at layer 4 and layer 5, we start to see other types of features that are activated that are more composite. So for example, here in layer 4, we start to see faces of animals or faces of dogs. And then at further levels, you can see that they've got more structure. So for example, layer 5, you can see something that's focusing on a particular eye, or in some cases, a more complex pattern here that's composed of more fine-grained patterns. You can see all the typewriter dots here are actually quite fine-grained. So this is what the convolutional neural network is doing. It's basically a specialized case of a neural network, but done in a way so we restrict it to have fewer parameters. The primary idea we can apply it to is, again, to images where features are local. We use a feature map and apply it to the same learn filter or convolution over the entire image field. We can see how that works over here. For example, if I have a convolution that we're trying to learn in this blue area, we first feed it the weights of the first 3 pixels, for example, and then we provide it with input from a shift of that. So just like we shifted in the last picture, we're going to shift the inputs over to x2, x3, and x4 and have the feed-forward network and the backpropagation retune the same weights, our tied weights that are being used over all of the different spatial subsamples of the image. Once we're done with that set, we again move it out of the way, and we train an additional number of times all the way through all of the different sliding windows over the image. So that's what we're doing here. We're sliding this particular window over the image and exposing the convolution to different areas of the image and building up these feature maps in a new layer of the network. So that's what the convolutional layer does. We can then subsample or pull these together to create smaller, lower resolution maps that go over a larger portion of the image through our subsampling or pooling layer, and then repeat these operations in separate layers. At the end, we might fully connect our network so as to get a classification output here, which could be, let's say, using a softmax output. So what do those subsampling or pooling layers do? Well, it's actually very simple. Pooling is just taking, for example, a feature map like this one that was computed using the convolution, and then deciding what we're going to do with all of these features. So with a 2x2 filter and a max pool, meaning that we just take this 2x2 grid and populate the largest maximum output for each of these cells, which are going to be ending up on the 2x2 filter that we created on the right hand side. We say this has a stride of 2 because we miss out all those intermediate rectangles, those intermediate squares as we've drawn here. All of these we skip over because we have a stride of 2, so we're always going to be jumping 2 units at a time when we do the change. This type of pooling helps to downsample the data and helps to generalize our application so it's not specific to a particular location, and helps to find the same type of features at a higher resolution. And as we saw on the last slide, these are typically layered between convolution layers in a convolutional neural network. So we can see we're trying to learn different features here, exactly like we saw in the previous slide that showed the filters and their activations. And each time we go up, when we do some type of pooling, so these are max pooling layers here. Every time we do that, we are trying to lower the resolution of the image and find the features in the subsequent convolution layer at a larger size, meaning over a lower resolution image. We highly also encourage you to try the ConvNet JS demo that you can click on the hyperlink for the slides and try that out.